Hello, everyone, and welcome to another episode of Echo Live, brought to you by the Michigan Science Center's Echo Distance Learning Program. So, I am here in our distance learning studio today. My name is Paulette, and I'll be talking to you a little bit about a kind of complicated subject. Today, we're going to be talking a little bit about dark matter. So, if you haven't done so already, go ahead and introduce yourselves in the chat. That chat feature is going to be the best way for you to communicate with me throughout the program. I will be asking questions during our program today, so I feel free to answer them. Or if you have any questions for me, that chat feature, like I said, is the best way to go. So, like I said, I'm here in our Echo Distance Learning Studio today, and we're going to be talking, like I said, about a kind of complicated subject. We're going to be talking about dark matter. So, we need to think about this one. What is dark matter? So while we sort of think about what dark matter could possibly be, we can break it down using sort of the words that are part of it. So dark, meaning no light or unable to be seen, and matter, meaning has mass. So today we're going to be talking about that dark matter and how we figured out that something existed that needed to be called dark matter. Now, a lot of us know a little bit about gravity. Gravity is what keeps us here on the ground. But gravity also affects things out in outer space. So today I've brought in our gravity well. Now we've used this before on our Echo Live program, but we're going to use it to talk about a principle called gravitational lensing. But before we do that, we need to explore what's going to happen with this gravity well. So we can go ahead and change our camera view so that we can see the gravity well from the top down. You can see my hand right here on the top of our gravity well. And what we're going to do with this gravity well is we're going to add different objects to it. Now I have a couple of different objects. Let's go back to our front view here. I have a couple of different objects. I have this yellow ball right here. I have a tennis ball. I have a ping pong ball. I have a heavy lead ball, and I have a marble. Marbles are made out of glass. So we're going to take a look at what happens when we put these objects on our gravity well. So when we think about it, we can think that gravity is a force or something that actually moves and pulls things around it. And this could be our fabric of space and time. Now, this is actually an activity that you could do at home if you have a trampoline, or if you don't have a trampoline, you can actually do it standing on your bed. So we're going to try this experiment here with our gravity well, but you can try this as at home too. Let's go ahead and get rid of my virtual background so that we can see everything a little bit better. It's wanting to sort of attach to that black background. There we go. All right. So we're going to add these different objects onto our gravity well. So we're going to start with the largest of these objects. We're going to start with our giant yellow ball. And when we add this to our gravity well, not a lot happens. And that's because our yellow ball that we have right here is actually really, really light. You can kind of see the gravity well moving a little bit, but not very much. And that's because this yellow ball right here does not have a ton of mass. It's really big, but it doesn't have a ton of mass to move things around on our gravity well. A slightly more massive object might be our tennis ball. So if we add our tennis ball to this, we actually might be able to see it do something interesting. And you can kind of see that when we add our tennis ball to this fabric. This is actually just swimsuit fabric, and it's stretched over a giant hula hoop. But we have right here our tennis ball. When we add this to the equation, we can see a little bit of movement with our gravity well. So this object has a little bit of mass and is actually changing and bending the space around it. If we add in something that might be a little bit heavier, like our marble right here, if we add that in, we can actually start to see something really cool happening, because this marble is actually fairly dense. That means that its mass is large compared to its size. So we can actually start to see some bending happening, especially here in the front. That bending is pulling the space around it, and that is what we're sort of seeing as the force of gravity. Now we're going to move on to our largest object that we have and our most massive object so that we can see everything a little bit better. So here I have a ball. We've actually covered it up with a yellow balloon so that we don't actually touch the surface of it. But you can see that that really pulled down on our fabric. So the more massive an object, the more it changes space around it. Now, when we're talking about something like light, light doesn't actually have mass, but light is one of those things that actually just follows the fabric of space. So light follows this fabric of space, and we can see something interesting happen when we introduce a smaller mass. So here we have a smaller marble, and if we introduce that into our system, we can see it orbit around our larger mass. Let's try that a little bit harder. There we go. So we're adding some, we can see it orbiting around our larger mass, and I'm trying not to give it too much velocity because then you won't be able to see it. But our mass orbits around our larger mass. So that would be like our Earth orbiting around the sun. But in light, there isn't enough mass to actually make something like light, which moves really fast. There isn't enough mass to make that light orbit around because, well, light itself doesn't have mass either. But what it can do is it can actually tug slightly on the light itself. So as our marble comes in, if we pretend that this marble is light, I know that it doesn't have, or it does have mass and light doesn't have mass, but this is going to be sort of our easiest way to talk about it. As it comes in, it'll actually get pulled into this field right here and pulled around the object. So if we have something that's back behind here, it might get thrown off this direction, or it might get thrown off this direction, depending on what direction it's sort of going around or which side it's closer to. This is something that we call gravitational lensing. So gravitational lensing is kind of a complicated subject because it's hard to think about massive objects being able to pull on something like light. But these massive objects that we have here, if we look at our marble, we're actually able to see that it's able to pull on a lighter object. And it's even able to pull on an object like light because light travels along this black space that we have right here. So, gravitational lensing is something that we have actually been able to observe when we take a look at things out in real space. So we've been able to observe gravitational lensing around really super massive objects. We've been able to observe it around objects like galaxies, and even stars. We've been able to observe gravitational lensing happening around our sun during a solar eclipse. So let's go ahead and take a look at what I mean by gravitational lensing. We've been able to see it here at our gravity well, but we'll look at it a different way because it's such a complicated subject. We're going to look at these things in a couple of different ways so we can understand them a little bit better. So let's go ahead and take a look at one of these images that I have, and we might be able to see it a little bit better. So this is what we're talking about when we say gravitational lensing. So what happens to the light from this distant galaxy right here is that it goes around the cluster of galaxies or the supermassive object that we have right here. So when it goes around that cluster of galaxies, we're actually able to see that galaxy not behind the cluster of galaxies because they're blocked from view, but we're actually able to see them off to the side. So they'll actually appear in the very edges of our images when we look at these images in space. So this gravitational lensing, like I said, we're able to see it with things that we are able to see out in space. So like clusters of galaxies, single galaxies. We've even been able to see gravitational lensing happening around our sun during a solar eclipse. Let's go ahead and take a look at one of our examples of gravitational lensing in our virtual planetarium. So here we're using Worldwide Telescope. Worldwide Telescope is, of course, a free program that you can use at home if you are so inclined. And this is a really great program to take a look at some of those deep sky objects. Worldwide Telescope is full of images from Hubble Space Telescope and from all sorts of other telescopes so that we're able to see things in different wavelengths of light, as well as being able to see things in visible light, mostly from our Hubble Space Telescope. So we're going to take a look at one of our first objects, and this one is LRG. So let's go ahead and take a look at this object and what it looks like close up. All right, so here we have LRG. There it is. So this is a fantastic example of where we can see gravitational lensing happening around a massive object. So instead of being able to see a galaxy behind these two galaxies right here, the image of the galaxy that's behind it actually gets distorted and pulled around into this sort of circular shape that we see. This is actually lensing the light from these galaxies around the massive object. So that's why we call it, again, gravitational lensing. We're able to see this, and we know that these galaxies right here are pretty massive, and that's why we can see that gravitational lensing. Makes sense. Light and other things, but light specifically gets lensed around a massive object when the light is coming from behind it. Awesome. Cool. Makes sense. Something that we definitely expected. The next one that we're going to go to is Able 370. And you might wonder, who on earth names these things? Most of these things are named by in catalogs. So for example, Able is probably a catalog of things that were discovered by a guy named Able. Usually it's a guy. But we're able to see, as we zoom in, some more of that gravitational lensing. So we can see another cluster of galaxies here in the center and the light lensing around those galaxies. Okay, cool. Something we would have expected to be able to see. Now we were noticing these things around massive objects and we're like, awesome, something we would have expected. And then a few years later, we were able to actually test this theory on stars around our sun. But we were also noticing some gravitational lensing in places that we didn't expect. So for example, when we take a look at, we're going to search for another one. When we take a look at the Coma cluster, right here, we're going to see something kind of weird. So when we get a close-up view, we're able to see some gravitational lensing happening. We actually have several different copies of the same galaxy. You might ask, how do we know that these are the same galaxy and not just a different galaxy? We know that they're the same because they have the same spectra or the same fingerprint, essentially, when we look at their light. Their light is exactly the same coming from all of the different ones, so we can tell if they're the same or if they're slightly different. So we're able to see a number of the same galaxy around this image right here. And that's something that was really weird, because when you take a look at this, there isn't something really obvious here in the middle that gives us our mass. It's not like there is a giant cluster of galaxies, but it doesn't give us enough mass to see all of these different copies of the same galaxy, like this one and this one, that we see lensed around this area. Okay. All right. So this is an area that kind of stumps scientists, because we look at it and we go, all right, we know what makes sense. And then the observations that we are making are going against everything that we thought we knew. Okay, so let's go ahead and take a look at another one. We're going to take a look at the bullet cluster. And this one is by far my favorite. This bullet cluster, we've actually been able to look at in several different types of light. And so we're able to get a better idea of sort of what's going on. All right, so when we take a look at this bullet cluster, we can actually see where the concentration of matter or mass is. The concentration of mass is sort of right here and right over here. Cool, makes sense. But what we found when we looked at things like gravitational lensing and some other things was that the matter was actually not where all of the mass was concentrated. When we looked at this area using visible light and X-ray light, we actually found that even though the matter, the stuff that we could see, was centered right here, our mass was actually centered around these blue spots right here. So when we were taking a look at this, scientists kind of went, whoa, this is weird. This is something we didn't expect. This bullet cluster was discovered a couple of years ago, or quite a few years ago. And we were, again, able to see it in visible light. Okay, there's all of our mass, there's all of our visible light. And X-ray, so that we can actually see where the matter or the mass of this is sort of originating. And it almost looks like these are two galaxies or two clouds of gas that collided at some point, because we have sort of one going off in this direction, one going off in this direction. We have a lot of bright light happening here in the center. But these two spots right here, the stuff we can't see where the mass is actually centered, doesn't look like it interacted at all. It looks like those two massive objects just kind of went right through each other and never interacted with each other. This definitely confused scientists, and it confuses us to this day. We've decided that there has to be something out there. There has to be something that exists other than what we call matter. There has to be something that has mass, which makes it matter, that we can't see. So we call it dark matter. Now, this is just one of the ways that we observed dark matter in the nighttime sky with some of the objects that we were looking at. The other way that we observed dark matter was actually by looking at galaxies. So we took a look at some galaxies, and actually this was one of my favorite female scientists, Vera Rubin. Vera Rubin was a Jewish scientist from here in the US, and she was taking a look at galaxies. And what she expected of those galaxies, she expected to see that the galaxies, the velocity of the stars or the stuff that we see in the outer part of the galaxy, would drop off. That's what we expected to see because that's what the physics tells us. If you are on, say, like a disk, and so it's something solid, then the further out you go, your velocity actually speeds up. But if you are in a galaxy, something that is not solid, you would expect to see the velocity decrease proportional to the distance away from the center and the mass. Well, that's not what we were finding. We actually discovered, or she discovered specifically, that the observations near the center of our galaxy here made sense. But the observations in the outer part of our galaxy sure didn't make sense at all. The observations that we were seeing in the outer part of our galaxy, this is what we expected. We expected a peak right here where we have most of the mass, and then a slight drop off as we continue on. But we were seeing that it's actually increasing. Scientists were super confused, and Vera Rubin discovered and said this must be that dark matter that we were talking about. So that dark matter is actually out here in the halo of our galaxy and causing this expansion or increase in the velocity that we're seeing. Well, so we were able to observe dark matter in our universe out in space. Now you might ask, okay, we were able to observe it out in space. Have we ever observed dark matter directly on the Earth? What do you think? Have we ever observed dark matter directly on the Earth? And the answer is maybe. We might have detected dark matter directly on the Earth. There are actually several different researchers that are looking for dark matter. I actually worked for one of these research groups in College Station, Texas. I went to Texas A&M for a semester and did research trying to find dark matter. I was building detectors to try and find dark matter in the future, or as we sort of built these detectors. I worked for the Cryogenic Dark Matter Search, and the Cryogenic Dark Matter Search has maybe discovered a couple of things that might have been dark matter. We don't know. There are also some other things out in space that, or other research groups that have been working on some other things. And we think that they're either weakly interacting massive particles or massively compact halo objects, or we honestly don't know. Because we've never been able to directly detect dark matter, it is one of the many mysteries of the universe that's going to take the next generation of scientists to figure out. Dark matter is a very, very interesting topic that we don't know a ton about and is going to sort of sway our research in the future, because dark matter actually makes up more of our universe than regular matter does. Regular matter, the stuff that we can see, only makes up about 4% of our universe. And of that, we've only seen 1% of our entire universe because of how far we can see with telescopes. Yes, Evan from Texas, go Aggies, gig 'em. Definitely, like I said, went to College Station at Texas A&M for a semester doing research there, specifically working on this cryogenic dark matter search. Now, it is going to take the next generation of scientists to figure out, because it is a mystery of the universe. And some of this stuff can be hard to understand. So that's one of the reasons why you have to stick with math in school. I know a lot of people don't like mathematics, but it is a huge part of science, and specifically physics and astronomy. And you also have to be interested in it and work really hard. That's what I did in school. Is I worked really, really hard, and even though I wasn't the best in my math classes and my science classes, I was still able to do that research because I was enthusiastic, and I sought these types of things out, and I worked really hard to get to the research projects that I had. So dark matter is a mystery. We think it could be a couple of different things, like I said, weakly interacting massive particles over massively compact halo objects, but we really don't know. We know that we've been able to observe it indirectly, but we've never actually been able to see it with our own eyes. So one of the reasons that I love dark matter so much is that it actually gives us an excuse to continue to research, because we don't know what it is. Could be a lot of different things. We just know that it doesn't interact with regular matter, and that it is really, really massive. So it really pulls on that space around it. I know we went kind of fast and we went over some kind of complicated subjects today, but if you have any questions, feel free to type them into the chat. This is a great time to thank our wonderful sponsors of the Echo Live program. We have, of course, Ford and Denso. They've been supporting us since the beginning of our Echo Live program. And we're here for the next couple of months to support you and supply. I'll be here to do more virtual planetarium programs. Anna will be here to do more programs throughout the rest of our year. And we'll even have some special guests coming up in the relatively near future. So make sure to tune in and continue to watch us on Echo Live Tuesdays and Thursdays at 2:30 Eastern. If we do change that at all in the near future, we'll make sure to put it on our Facebook page, so keep an eye out for that. We're almost done with our Summer of Science here at the Michigan Science Center, so we have just a couple more days to come into the Science Center for free. But after Labor Day, we'll still be here. We'll be changing our pricing and adjusting things for our post-COVID world. So we hope to see you come to the Science Center if you're able to. And Evan from Texas, it was great to see you today. I'm so happy that you are still joining us, even though virtual school is happening. I think that our program is just as good as a virtual school. So I'm glad to see you here with us still. All right, so seeing no questions, I want to thank everybody so much for joining us today here on Echo Live. And keep joining us Tuesdays and Thursdays, 2:30 p.m. Eastern Time.